video, we're going to be talking about the Born-Oppenheimer Approximation. This is going to be an important approximation as we put together model systems of molecules. So let's take the very simplest molecule we could make. It has 3 quantum particles, and that is the diatomic hydrogen ion, H2+. It has 2 nuclei, and each nucleus really only contains, on average, 1 proton, because that's the most common isotope of hydrogen. And then there's 1 electron shared between them because of the positive charge of this molecule. So we could think about, of course, defining a Hamiltonian for this system. It's going to have kinetic energy operators and potential energy operators, so k hat plus v hat. And if we start with k hat, we can think about each of these quantum particles has the ability to move. So it's going to have a kinetic energy operator associated with it. So we can say that k hat sub e is the kinetic energy of the electron as it moves. K hat in 1 is the kinetic energy of one of the nuclei as it moves, and k hat in 2 would be the kinetic energy of the other nucleus as it moves. Now let's think for a minute. The mass of a proton is 1.672 times 10 to the negative 27 kilograms, and the mass of an electron is about 9.109 times 10 to the minus 31 kilograms. What's the ratio of the mass of the proton to the mass of the electron? So that ratio is approximately 2,000, right? There's 3 orders of magnitude difference, essentially, between the mass of the proton and the mass of the electron. So let's think of something else that also has approximately this ratio of masses. Did you know that the mass of a bowling ball is also approximately 2,000 times that of the mass of a ping pong ball or a table tennis ball? So the bowling ball I used here was about an 8-pound standard issue bowling ball. So we also have the same ratio here. So imagine with me for a moment that we have both a bowling ball and a ping pong ball. If I have both of them sitting on a desk or sitting on the floor, and I go and flick both of them with my finger with approximately the same force, what would happen? So the ping pong ball would probably start rolling across the room. The bowling ball probably wouldn't visibly move, although I might bruise or break my finger trying to flick it to get it to move. So the point here is that heavy objects and light objects don't behave the same when the same force is applied to them. And that's due to their mass, right? They have force due to their mass. So here we can think about the same kind of situation with the proton and the electron, or with the nuclei, right? Because the nuclei are only going to get heavier compared to the electron as the atoms get bigger. Here we can think about if we apply the same amount of force to move the nuclei or to move the electron is going to move very quickly and very far, well before there's a noticeable movement of the nuclei. What this allows us to do is neglect the kinetic energy terms of the nuclei because they move so slow compared to the electron. So whenever we have molecules, the Born-Oppenheimer approximation allows us to neglect the kinetic energy terms due to nuclear motion. And while this may not seem like a lot as molecules get big, it is something, right? It allows us to simplify the system a small amount, and that small amount turns out to be fairly significant. So now let's look at the potential energy operator terms. So we'll have 2 terms due to the electrostatic attraction of the electron to each of the nuclei. So we'll have V hat 1e would be the electron attracted to one nucleus. V hat 2e would be the potential energy operator due to the electron being attracted to the other nucleus. And then we'll also have some V hat 1, 2, which would be the electrostatic repulsion between the 2 nuclei. Remember that electrostatic or Coulombic potential energy operators always take the form of the charge of particle 1 times the charge of particle 2 divided by 4 pi epsilon naught, which is the permittivity of free space, times the distance between particle 1 and particle 2. So if we're thinking about an electron and a proton, the charge of the electron is negative 1e, and the charge of the proton is positive 1e. But if we're thinking about two like-charged particles, we'll get a product that is positive as opposed to negative.